A very good morning to all of you. In this session, we will discuss about propositional logic and first order logic, that is predicate logic. First, we will discuss propositional logic. Propositional logic deals with the statements that have a clear answer, that is either true or false. A declarative sentence that can be true or false. So that means declarative means it is a statement, not a question or not a command. And it must have only one truth value, either true or false. So we will see some of the examples. First one is it is Sunday. So this is a proposition because today it can be checked and decided as true or false. Then second one, that is sun rises from west. So that is a false proposition. Even though this is false, it is still a proposition. That means logic does not care whether it is correct, only that it has a truth value. So false statements are also propositions. Then the third example is 3 plus 3 is equal to 7. That is also a false proposition. This is mathematically wrong, but it is still a proposition because it is clearly false. Then the fourth example is 5 is a prime number. This is a true statement, so it is a proposition. So we can say that any sentence that can be judged as true or false is called a proposition. So the propositional logic studies declarative sentence that can have a definite truth value, that is either true or false. We can see the connective symbols and first one is and operator, that is its technical term is conjunction. Here we can represent as P and Q. Next is or disjunction, we can represent P or Q. Next is implication, that is implies, the operator is implies operator, P implies Q. Then biconditional, that is if and only if, P if and only if Q. Then not operator, that is negation, that is not P or not Q. Next we can see the truth table. So you may be already studied the truth table in digital electronics. First one is P and not P, that is not operator. When P is true, not P is false. When P is false, then not P will be true. Then if next is P or Q. So P or Q means either P or Q is true, then P or Q will be true. So you can see first case both are true, then P or Q will be true. Second case P is true, Q is false, then P or Q will be true. Third case P is false, Q is true, then P or Q will be true. And both are false, then P or Q is false. Then the next case, that is P and Q. Both are true, then P and Q will be true. Here in the case of P and Q, if both are true only, P and Q will be true. All other cases it will be false. You can see here, second case, P is true, Q is false, that is false. P is false, Q is true, then P and Q will be false. Both are false, then P and Q is false. So here in this slide we will discuss P implies Q and P if and only if Q. So these two truth table we will explain with example. For that we are considering one example. Here let P is today is Sunday and Q is we have just is specified here. Here P and Q are just short names for long English sentences. So this makes the logic easy to write and analyze. And here first we can see P and Q. So P and Q means today is Sunday and we have guest. So here the statement is true only when both P and Q are true. We have already seen the truth table. So today must be Sunday and guest must be present. So next is P or Q. So that is today is Sunday or we have guest. So this is true if at least one of them is true. So that means in logic or includes both can also be true. Next is not P. This is not Sunday. So it simply reverses the truth value. So if P is true, then not P is false, and P is false, then not P is true. Next is implies. So we will discuss in detail implication. That is P implies Q. So if today is Sunday, then we have guest. So this is a conditional statement. It does not say guests come only on Sunday. It says Sunday implies guest. So if P is false, then the statement is still logically true. So here you can see that the truth table. If P is true, Q is true. That means it is Sunday and we have guest. So P implies Q is true. Then P is true and Q is false. That means today is Sunday, but we don't have guest. So that means P implies Q is not correct. Because if today is Sunday, then we should have guest. But here we don't have guest. So that is false. And third case, today is not Sunday, but we have guest. That is also no issue because P implies Q means if it is today is Sunday, then we should have guest. But today is not Sunday, then we may have guest. It is not, we are not bothering about it. So then also here P implies Q is correct. Then both are false. Then also P implies Q is correct because today is not Sunday and we don't have guest. But if today is Sunday, then we have guest. So that is true. Then we will see by conditional. That is if and only if. So today is Sunday if and only if we have guest. If we have guest only, we can say that today is Sunday. So this means both directional. P implies Q and Q implies P. So either both are true or both are false. So that means here you can see if both are true, it is true. Both are false, it is false. All other cases, one is true and other one is false. In both cases, that is false. So that means if today is not Sunday, today is Sunday, but we don't have guest means this is not correct. Today is not Sunday, but we have guest means also it is not correct. So the logical connectives allows us to combine simple proposition to form complex logic statements actually. So here we can see another example. T means it is hot, Q means it is humid, and R means it is rainy. So we have example P and Q implies R. So that means P and Q means it is hot and humid. So that means it is rainy. Then Q implies P means Q is it is humid. It is humid means it is hot and it is hot. Then we will discuss representation of simple facts. So here we will see how real world facts are represented inside in a computer using propositional logic. So real world facts are represented as logic propositions written as well-formed formulas, that is WFF, well-formed formulas in proposition logic. So here in real life we speak in English, but computer do not understand this English. So we have to convert the real world facts into logical symbols called a proposition. So these symbols that must follow some proper rules that is called a well-formed formulas. So here we will see example. You can see that here we have it is raining. That is an English sentence. Then corresponding WFF or well-formed formula is called is raining. So it is raining means raining. Instead of writing the full sentence, we use a simple symbol called a raining. So this symbol can be either true or false. Next is it is sunny. We can write it as sunny. Then it has a true value, either true or false. It is windy. Then we can write it as windy. So windy is a simple proposition representing a real world condition. So each symbol represents one simple fact. Next you can see if it is raining then it is not sunny. So that means now we are connecting two facts here. So and this here you can see raining means not sunny. So this arrow indicates if then. So and here it is raining then it is not sunny. So this entire expression is also called a well-formed formula because it follows some logical rules. So Here, the simple real world facts are converted into logical symbols and formulas that a computer can understand. Here, we can see representation of simple facts. We can see the example. Socrates is a man. So we can write it as Socrates man. Then, Plato is a man. Plato man. All men are mortal. Mortal man. So, in propositional logic, each sentence is treated as a single symbol. So, the system does not look inside the statement. Here, each statement is treated as a atomic, you can see separate atomic proposition. So each line is independent. So the system thinks these are completely unrelated facts. So there is no internal structure is there. The logic cannot see world like a Socrates, man or mortal. It only sees the symbol like a Socrates man. So there the system cannot see similarities between Socrates and Plato. So even though both are men, you can see Socrates is a man and Plato is a man. So both are men. The system cannot recognize this similarity here. And next point you can see no logical connection exists between a man and B mortal. So that means the system does not understand that men are mortal. So it means that man and mortal are it considered as or it treats as unrelated words. So here the conclusion cannot be derived because of this limitation. We cannot infer new facts actually. So even if all men are mortal, the system cannot conclude that Socrates is a mortal. So we know that Socrates is a man. That means all men are mortal means you can simply say that Socrates is a mortal. But here in this representation, Socrates man, Plato man, mortal man. So if you represent like this, it is not possible to find the conclusion or derive the conclusion. Even if all men are mortal, the system cannot include Socrates is a mortal. So this is actually the limitation of a proposition logic. So therefore, the proposition logic is not sufficient for representing complex knowledge. This is why we are moving to next one, that is first order predicate logic. We will see in detail the limitations of proposition logic. The first one is it cannot represent all, some, and none. So that means proposition logic can only say whether a statement is true or false. It cannot handle quantities like all, some, or none. You can see all girls are intelligent. Some apples are sweet. We cannot represent. Here we are talking about group, not a single fact. The proposition logic has no way to represent all or some. Next point is cannot handle variables. So that means proposition must be either true or false. For example, if there is a representation x is greater than 1, this statement is depending on the value of x. So without knowing x, we cannot say that it is true or false. So hence it is not a proposition. Then the third one is actually, third point, not powerful enough for all assertions. So that means the proposition logic treats every sentence as a single atomic symbol. So it cannot analyze the internal meaning of the sentence. And then next point is cannot represent properties and relationship. So that means here an example is given. Ram is the father of Shyam. So this is a sentence that expresses a relationship between two objects. So the proposition logic cannot represent such relations. So here it will just take it as Ram father Shyam, one symbol. So the logic does not understand who is related to who. It will only represent Ram father Shyam as a one word. What that is a one represents one symbol. So because of this limitation, propositional logic is insufficient for representing complex real world knowledge. To overcome this limitation, we use first order predicate logic. Next, we will see first order predicate logic. First order predicate logic is another method of knowledge representation used in AI. So it is an extension of propositional logic. The propositional logic only talks about facts. But here, in this case, there is first order predicate logic that talks about objects, their properties, and relationship. So we will see the first order predicate logic is actually more powerful because it can describe real world information in a structured way. So it does not treat everything as a single symbol. We have already seen in the proposition logic, everything we are representing it as a one symbol. So, but here it is different. Here we will see first order predicate uh, models the world in terms of first one is objects. So objects are things with individual identities. For example, here you can see Socrates, Plato, book, student one. So each object represents a real world entity. So next is properties of objects. So that we can call it as predicates. So we can see this example, man Socrates, student Rahul, and red car one. So the properties describe the characteristics of the object. They tell us what an object is or what it is like. So man Socrates means Socrates has the property of being man. Then student Rahul means student has the property of being a student. Then next point is relations among objects. So here you can see teacher comma student, parent John comma Mary, enrolled student comma course. So this relations describe how two or more objects are connected. So parent John comma Mary means John is the parent of Mary. Teacher comma student means teacher teaches student. So this representation is not possible in the case of propositional logic. And the fourth point is functions. Functions are special type of relation. So for each input, a function gives only one output. So here you can see father of X, age of person. So age of person gives exactly one age for each person. Then father of X gives one father for a person. So we can say that first order predicate logic allows us to represent objects, properties, and relationships and making it expressive than the proposition logic. So one more point, first order predicate logic is another method of knowledge representation used in AI, but this is an extension of proposition logic because we have already seen that propositional logic will consider only the facts, but here we will consider objects, properties, relations, and also the functions. Then next is basic elements of first order predicate. So here the first one is constants. So constants are used to name specific objects in that particular domain. For example, you can see A comma B comma D 33 are example. We have already seen Devi, Rahul, Ajay. So a constant always refers to a one fixed object. Then second element is variables. So variables are used when we do not want to name a specific object. We can call it as X, Y. So variables can represent any object in the domain. Next is functions. Functions actually map objects to object. So that means for each input, there is exactly one output. We have already said father of X, age of person are functions. Then the fourth element is terms. So terms are expressions that refer to objects in the domain. So it can be a constant, can be a variable, or it can be a function applied to arguments. So, for example, Ravi, X, father of Ravi, all these are terms. Then atomic sentences. So, atomic sentences are the simplest statement that can be true or false. So, here you can see the example. Ravi and Ajay are brothers. So, brothers, Ravi, comma, Ajay. Chingy is a cat. So, cat Chingy. Chingy. So, that corresponding to propositional symbols, PQ. So, here Uh, so these are actually similar to proposition symbols P and Q, but with some structure. Then here in this representation, brothers Ravi, comma Ajay. So this represents a relationship between two objects. But cat Chingy, that is actually it is actually similar to a propositional logic. Next is quantifiers. So quantifiers actually specify how many objects in the domain satisfy a predicate. So there are different types of quantifiers. You can see the universal quantifiers and existential quantifiers. We will see. So here quantifiers tell us how many objects satisfies a condition. So in the case of universal quantifier, we are representing it as all x, all x. This symbol is used for representing universal quantifier. So this means that uh, P is true for all values of x. And for all x, dolphin of x implies mammal of x. That means all dolphins are mammals. For every x, if x is a dolphin, then x is a mammal. Then existential quantifier means uh, this means P is true for at least one object. So here it is given existential quantifier mammal of x and lays x of x. So there exists a mammal that lays egg. So there exists at least one mammal that lays egg. So the first order predicate actually allows us to represent objects, properties, relationship, and quantifiers in a precise way. So we will see the examples. Here we can see how the English sentences are converted into well-formed formulas in first order predicate logic. The first example you can see Marcus was a man. So it can be represented as man Marcus. So here Marcus is a constant representing a specific person and man is a predicate representing a property. So Marcus has the property of being man. Second line, Marcus was a Pompeian. Here we can represent it as Pompeian Marcus. So it is also a simple fact. The predicate Pompeian applies to the object Marcus. Next is all Pompeians were Romans. So here we are for all we are representing using the universal quantifier. You can see this is the symbol for universal quantifier all x. So if any person is a Pompeian, then that person is a Roman. So this kind of general rule cannot be expressed in propositional logic. This we can express in first order predicate logic. The next line, every gardener likes sun. So every gardener, for every means all. So here you can see for all x, gardener of x, if x is a gardener, then he likes sun. So likes x comma sun. So here for every x, x is a gardener, then x likes the sun. So here x is a variable, sun is a constant, and likes is a relation. So all these are well-formed formula because they follow the syntax rules of first order logic. So first order predicate logic actually allows us to represent individual facts, general rules using predicates and quantifiers. Then we will see more examples. Here you can see all purple mushrooms are poisonous. For all representing all, we have we can see here universal quantifier for all x, mushroom of x, and purple of x. You can see all purple mushrooms. So we are writing if x is a mushroom and x is purple and we are representing using and because all purple mushrooms. So it should be mushroom and it should be purple. So then that means are poisonous. So that means implies poisonous of x. So for all x, then x is a mushroom and x is purple means it is poisonous. Then everyone is loyal to someone. Everyone. For representing everyone, we are using universal quantifier, all x. It is loyal to someone. For someone, we are representing using existential quantifier, that is some y. Then What does it mean? Everyone is loyal to someone. So loyal to x comma y. Everyone loves everyone. Both are everyone. That's why we are writing for all x, all y. Then loves x comma. Then everyone loves everyone except himself. So everyone loves everyone we already represented. For all x, all y loves x comma y except himself. Except himself. That means x don't like x, but x likes y. So how we can represent don't likes x, x comma x? So we can represent it using negation. You can see here not loves x comma x. Every student has a book. So that means all students have book. So for all x, x is a student. So that means student of x implies then it has book, he has book. So how we can write book? We can represent it using another book. If it's specified any particular name, then we can represent as a constant. Otherwise, we can represent it as a variable. So it is written for some y. It has a book, right? Not all book. It has a book. So some y book y. Then if then has x comma y. So if student is x, if x is a student and y is one book, any book, then that means x has y. Example you can see here. Ram is the father of Shyam. It represents a relationship. So Ram is the father of Shyam. So we can see here father Ram comma Shyam. It represents a relationship. So Ram is the father of Shyam. Then everyone likes ice cream. So for everyone, for representing everyone, we have all X. For all X, then likes ice cream. So likes X comma ice cream. Then someone likes coffee. The someone means existential quantifier. So some white likes X comma coffee. All doctors help people. So representing all, we have universal quantifier. For all x, then x is a doctor. So doctor of x implies that help people. So if he is x is a doctor, then x helps people. So he can see here helps x comma people. Then there exists a teacher who teaches all students. So if x is a teacher, then x teaches all students. For representing students, all students, we need y and teacher. Then we are representing it using it is a teacher. So we are using existential quantifier. So here you can see some x. That means there is only one teacher. There exists a teacher. A teacher. Some teachers that teaches all students. So that means some x, teacher of x, and all y, student of y implies teaches x comma y. So one teacher and all students teaches x comma y. Every father is a parent. For every representing universal quantifier. For all x, fathering father of x comma y. So x is the father of y. That means he is the parent of y. So parent x comma y. Then another example we will discuss. All cities are in some country. For representing all, we have universal quantifier. For all x, city of x implies some country. Some country means existential quantifier. So we have some y, then y is a country and in x comma y. So that means all cities are in some country. So x comma in x comma y. So there y is a country and x is a city. So all city means for all x and some country means some y. Then our first example we didn't discuss. Some birds cannot fly. So that means x is a bird. So some. So existential quantifier x, bird of x and it cannot fly. Not we are representing using negation. Negation can fly of X. So that means some birds cannot fly. Every student who studies passes the exam. So all students. For all X, student of X, that means studies X implies, so X is a student and his studies implies that passes X comma exam. X will pass the exam. All doctors who work in hospitals are professionals. For all X, we can represent it using a universal quantifier. He is a doctor, so Dr. X works in hospital. So works X comma hospital. So X is working in a hospital. That R we are representing using implies. Implies X is a professional, right? So, so professional X. Then you can see next one. All birds that cannot fly are animals that live on land. So for all X, we are representing using for universal quantifier for all X. X is a bird and that cannot fly, right? So not can fly. So then so cannot fly is that negation of fly. So no negation of can fly of X are animals. So implies animal of X and that lives on land, right? So lives on land. Lives on land. Who is living? X is living. So for all X, if X is a bird and X cannot fly, implies that X is an animal and it lives on land. Then we will see not all students take both history and biology. For not not all students means not of universal quantifier, not X. When X is a student, then implies that X can take history and X can take biology. So takes X comma history and takes X comma biology. No person like a smart vegetarian. No person like a smart vegetarian. So here you can see for representing X, we are putting universal quantifier for all X because no person likes a smart vegetarian, likes a smart vegetarian. So that means all person. So for all X and Y is a vegetarian and Y is smart implies that not likes X comma Y. So that means X is a person and Y is a vegetarian and Y is smart. That implies that this X don't like Y. So not likes X comma Y. There is a woman who likes all men who are not vegetarian. So there is a woman. So that means some Y. So some X. Woman of X. X is a woman. And what is his property? Who likes all men who are not vegetarian. So that means there is a man. So for all men we will represent using universal quantifier for all Y man of Y and also who is not vegetarian, right? So not vegetarian Y implies that what it means here it is given who likes all men. So likes X comma Y. Then next is the best score in history was better than best score in biology. So here you can see we are for representing that is who got best score in history. For representing that we are putting for all X. Then for all Y, that means students studying biology, students studying history. So best score history comma X. So X got very good score in history. And best underscore score biology comma Y. So Y got good marks in biology. Then who will be better? So better X comma Y. So who study history is better than the who study best score in biology. All Romans were either loyal to Caesar or hated Caesar. So that means for all X, X is a Roman of X, either loyal to Caesar or hated him. So implies that where we are representing using implies. Then loyal to x comma Caesar, or it indicates that or. Then hated x comma Caesar. Then next is people only try to assassinate rulers they are not loyal to. So people means we will represent this for all x. X is a people and y is a ruler, and try to assassinate x comma y implies that when they will try to assassinate, not loyal to. So we can represent not of loyal to x comma y if x comma y. So y is not loyal to x, then x will try to assassinate. Then next is anyone who is married and has more than one spouse is a bigamist. So anyone who is married. So that means for all x who is married, x is married, married of x, and then number of spouses. You can see there is a function called GT. So GT of that is represents greater than GT of number of spouse of x comma 1. So x is married and x has number of spouses greater than 1. That implies, so it is easy. It is not IA, it is easy. Easy will represent using implies bigamist. You can fool all people some of the time. So you can see for all x, all the people means all x. Some of the time we will represent using some y, some t. Then x is a person implies that time is t and can fool x comma t. Thank you.